In order to optimize that objective function, we first need to determine the boundaries for the feasible region. In order to do that, we're going to look at a system of inequalities, and we're going to find their points of intersection. In this case, we have 4 different inequality statements. Switching over to Desmos, we'll plug these in. We have 4x plus 9y is less than or equal to 36. 8x plus 6y is less than or equal to 48. X is greater than or equal to 0, and y is greater than or equal to 0. We're graphing all 4 of our inequalities here, and what we need to do is find the region where all of those shaded areas overlap. To me personally, that is a challenging thing to do because all of those colors kind of blend after a while. So I'm going to give you a different technique to try here, which is to change these first 3 inequality statements to equations. And then what we're going to do is leave the last one, y greater than or equal to 0, as an inequality, and we're going to introduce some statements inside a pair of curly braces. What this is doing is giving constraints to this last inequality statement, but you'll see what happens as we type these in. What we'll do now is re-input each of those inequality statements inside its own set of curly braces. And what we're doing, or what we see as we're doing that, is the shaded region starts to change as we update our definition for which section of the graph that we want shaded in. The end result here is that we have this polygon area shaded in. That is our feasible region that we want to consider. So what I've done with those extra statements and that extra typing is just simplified this process of identifying where these regions overlap. Now we can identify these different points of intersection. We see that we have one point at 0, 4, one point at 6, 0, and our point of intersection of those 2 lines at 4.52. If we pay attention to this last piece of information that we have in the directions, we want to round all of our coordinates down to the nearest integer as needed. We'll see that come into play as we get into applications because we can't have a fraction of a person, a fraction of an item. So we're going to round those values down to the nearest integer, meaning our points of intersection will be 0, 0, 0, 4. Instead of 4.52, we're going to round that down to 4, 2, and 6, 0. Then we can plot those points. And now we've constructed the boundaries for our feasible region. And we have our corners or test points that we could apply, that we could plug into an objective function to find out when it was either maximized or minimized, depending on the problem. Let's go through that process again in example 4. And we'll start from scratch since we're getting used to some of these more complicated ways of entering things into Desmos. Again, what I'm going to do is plug in each inequality, but I'm going to turn it into an equation. Until I get down to the very last one, I'll keep that as an inequality statement, and then in curly braces, I'm going to plug in each of those inequality statements. And we'll see that shaded region begin to change as we redefine where we want that region to be, what shaded region we want to include. Then we can zoom out to get that better picture and identify our points of intersection. We'll see that this is happening at, if we find that gray dot, sorry, it's not wanting to agree with me. Sorry about that. Not sure what's happening, but my device was fighting with me. If we tap on those gray dots, we can find those points of intersection at 0, 11, 8, 0, and 6, 4, once we round those values down to the nearest integer. Plotting those points then lets us establish this feasible region. And it indicates the test points, the corner points that we would use to plug into our objective function that we would want to maximize or minimize.